Yeah, sure. All right. So today, we kind of, I couldn't quite finish what I wanted to say last time. If you remember, so far we've looked at two different examples, one from CR geometry, one from symplectic geometry, where one can use attached holomorphic disks to answer, let's say, an analytic or a geometric problem. And I want to mention one more example. So I will still have to talk about some symplectic geometry. I'm not going to go into too many details here, but this is kind of really the main motivation towards where we are headed, which is towards totally real manifolds. So example 3, we'll start with the definition. So let M omega be a symplectic manifold. And again, the one that we are going to care about is MSCN, and omega is the standard symplectic form. So let L in M be a real submanifold of M. And for us, we are going to consider smooth submanifolds. So we are not going to worry too much about lower regularity. So let M be a smooth submanifold, and let J denote the inclusion. We say that in symplectic manifolds, one usually studies special kinds of submanifolds, and this is one type. We say that L is isotropic with respect to omega if, when I pull back the symplectic form onto L, this vanishes. Okay? And so remarks. One, this condition, so let's say star implies that the dimension, the real dimension of L has to be at most, so this is 2n, so it has to be at most half the dimension of your original manifold, and we'll see an analog in this in the complex setting. So we are, even though I'm stating all these results in symplectic geometry, we're really interested in the analog in the complex setting. And the second remark is that if we are working with a manifold whose dimension is half of the ambient manifold and it's isotropic, then we say that L is Lagrangian with respect, and always with respect to the symplectic form that we have fixed over here. Okay, so this is so I mean, I have not discussed that much about symplectic geometry and why do people care. As I said, it comes up in physics. Why do people care about Lagrangian submanifolds? So let me just say something which, I mean, maybe is not that useful from the point of view of what we are doing, but if you have a manifold, smooth manifold X, then when you look at the cotangent bundle, it has a natural symplectic structure.
X is any manifold.
X is any smooth manifold, and so this will have twice the dimension, so it will have even dimension, and so this can be given a natural symplectic structure over here, and I mean and then X will sit inside T star of X as a Lagrangian submanifold. So in some sense, there is this idea that basically every manifold is a Lagrangian submanifold of some natural symplectic space. I mean, we'll see another situation where this sort of pops up for us, but I mean, these are just remarks for people who've never seen any symplectic geometry and may wonder why we care about things like this.
In the complex manifold setting, what is J star W equal to 0 means?
So in the I mean, what does that question really mean? So it's going to imply that the manifold is totally real. Okay, so as soon as you have any complex, see, this is an area form. Let's take the standard one. We'll take Cn with the standard structure. Then omega is really the area form in each complex direction, right? So as soon as you have a complex piece in your manifold, the area is going to become positive. So I'll write down, okay, but it's not an if and only yet. So I'll write down that statement.
It seems like that you see standard symplectic structure. It is a subspace of it is the isotropic. It means when you apply J, it will not be orthogonal.
It need not be orthonormal. Yes. So let's see. Correct. So you will get right. You will get an orthogonal. Yeah. So maybe we'll come to that when we discuss CN, and we'll do this for linear subspaces. Yeah. Whereas that's not true for totally real subspaces. Okay. Good. So what did I want to? Okay. Yeah. Just a few examples. So here I'm taking my standard symplectic structure, as many of you have already started thinking about this. And so so this is sometimes referred to as the standard torus. It's just S1 cross S1 n copies of that. So this is not hard to check that this is Lagrangian with respect to the standard structure. So this is a smooth compact manifold. Sort of the local model for Lagrangian manifolds is really this subspace, which is imaginary Z equal to 0. So Z here is just my C1. Okay, so you can think of this as the local model for Lagrangian submanifolds. That's actually a technically sound statement in that you can locally always make it look like this. And perhaps for more examples, you just hit these with symplectomorphisms. So you can check that symplectomorphisms will preserve the property of being Lagrangian because they preserve the symplectic form. So symplectomorphisms. So by the way, this remark is a little bit interesting from the following point of view that I'll maybe be able to say this today. There are results where being Lagrangian says something about the convexity of a manifold. The correct notion of convexity is rational convexity, which I will not go into right now. If I get time, I will talk about it. So being Lagrangian says something about the convexity of the manifold, which is really more of a complex analytic motion. It's not really a symplectic motion. But the point is that when you hit this with a symplectomorphism, that's still going to preserve the Lagrangian property. So it's still going to give you something which is convex in whatever motion we are discussing. So symplectomorphisms somehow are also preserving this notion of convexity, which is actually coming from complex analysis. So that's kind of the interesting part of this final statement. But I'll make this more concrete when we actually come to that piece. Okay, so the result I want to mention is actually from the same paper of Kronov's. And so let M or L, and this is, I'm always going to take dimension to be half. So the real dimension is half the real dimension of the ambient space. Be a smooth, compact, Lagrangian. And something I haven't quite said yet, and this once I state this result fully, this will become a little bit more clear. I gave you an n torus, which is Lagrangian. In general, if you give me an n-dimensional compact manifold, it's not clear. There are obstructions to being able to embed it into Cn as a Lagrangian submanifold. So even though locally you have a model, there are lots of global obstructions in being able to write an n-dimensional real submanifold as a Lagrangian submanifold, even of the standard structure. So the ambient space has no topology. It's sort of the simplest symplectic manifold you can have, and yet there are. So this is not a trivial condition. Then Gromov says that there is a holomorphic disk, analytic disk attached. Okay, so this is a theorem which guarantees the presence of a non-trivial. So I mean, I maybe did not mention this in my definition, but I obviously look at non-constant holomorphic disks. Otherwise, this is a rather trivial statement. So just when we are looking at S1, I mean, I mean, maybe let's just draw a picture over here. And so then what he's saying is that there is some sort of loop which might have self-intersections. I may not draw it like that. So the loop lies on the manifold L, on this Lagrangian L, and this loop bounds a holomorphic disk. It may not be an embedded disk. It may have self-intersections. It may look quite bad, but nevertheless, it is an analytic disk in the sense that we have been discussing, and it is continuous up to the boundary, and the boundary is on this Lagrangian submanifold. And why this is sort of, this has many consequences. So, an important consequence, which was an open question for a while, where it exists, so here n is greater than or equal to 2, there exists no Lagrangian n spheres So we have this, let's say in C2, we have the standard torus that can embed as a Lagrangian submanifold. I've given you one example. You hit it by symplectomorphisms. You get many examples of Lagrangian tori. But something as simple as a sphere cannot be embedded. There's no Lagrangian sphere in CN. By the way, I just made a remark addressing Amardeep's question about what does this mean from a complex analysis point of view? And I said that it in particular implies that the manifold has to be totally real. So if you don't know what that means, I will define that today. But there are dimensions in which you can have totally real spheres. Okay, so there is a well-known example of a totally real 3-sphere in C3. So Lagrangian is doing more than that. And I was wondering if anybody knows how this implies. I mean, I'll run through the argument. It's a very brief argument, but how do you go from this statement to saying that there are no Lagrangian spheres? So suppose there is. Okay, so suppose I have a Lagrangian n sphere in Cn. Let me also write down something which maybe we have not bothered to, has not come up. So what is this? This is dx wedge dy1 plus dxn wedge dyn. And this is actually an exact symplectic form, which means it's D of a one form. So now I have to do this right. Okay, maybe there's a sign. I guess I don't need the other guys. So let me just do it this way. Right, so it's D of this one form. Okay. So let's say I have a Lagrangian sphere in Cn. So it has this holomorphic disk attached to it. Okay, so I have Cn such that f restricted to D is holomorphic and f is continuous up to the boundary. So this is continuous and the boundary goes inside this copy of Sn. You can also assume, this is something that we will see. So I'm assuming this is a smooth embedding. You can also for the moment assume that f extends smoothly all the way up to the boundary. Okay, so you can think of this actually as the smooth image, this entire loop as a smooth image of S1.
This is coming from Gromov's.
So I'm going to try and get a contradiction from Gromov's theorem. So I assume there is Lagrangian sphere. So the image, I'll just call it Sn for simplicity. Then Gromov tells me that there is, so Gromov says this.
So this has to be fully inside.
The disk has to be fully inside, doesn't mean much. Sn doesn't split the space. I mean, Sn is n-dimensional. So guys, please keep that in mind. This is going to matter a lot. In fact, this is going to, because what happens is that in dimension 1, in the plane, we are really talking about curves. You know, half the real dimension is curves. So that splits the space into two pieces. That's not the case. Our entire focus for the rest of this course is going to be on n-dimensional real submanifolds of Cn. And there is no notion of inside and outside. Okay. What can be proved is that this disk will not touch, the interior will not touch the sphere anywhere, but that's not important for this argument. Okay, so I have this disk, I have this boundary, I've written a form as B of another form.
So,
You have to, I mean, there's only one option, right? So what's going to happen is that when you pull back your standard form, this is going to be positive. I had written down an expression for this last time. This is absolute f prime, f1 prime square plus f prime. And we know this is a non-trivial holomorphic map, right? So f prime is going to be non-vanishing somewhere. So this is the area of the disk. This is always positive. But what is this? This is also d of f star of lambda naught. Let me call this lambda naught. Okay. Which, for the purpose of this discussion, you can push forward to the boundary and you get, so this is Stokes, you get this. And if this applies Stokes theorem, I mean, first I have sort of written this as, I can first do this on the boundary and then I can push it forward under F. Now, what can I say about this? This is a loop. I'm integrating a one form on a curve on Sn. So what should I be? Yeah, Sn is, you can contract all curves, right? So it has no h1 or even phi 1. That's why n greater than or equal to 2 is important over here. This, I mean, we have a Lagrangian one sphere in C. This is a contradiction. Right? So that means that there are no Lagrangian spheres, n spheres in Cn. And in fact, even in dimension 2, there are very few smooth surfaces that admit Lagrangian embeddings into Cn. I'll just leave this as a remark, and maybe I'll give you a reference. The fact that there are no Lagrangian line bottles in C2 with the standard structure was proved rather recently. It was proved in the 2000s. It was open for a while. It does not use this pseudo-holomorphic curve argument. This was done by Shevchishin and there's also a proof by Nemirovsky. But I mean, this is not pertinent to our discussion. But just to tell you that why this was such a sort of remarkable statement, because for a while there wasn't a very good understanding of what kind of n-dimensional compact manifolds admit Lagrangian embeddings into the standard structure. Okay, so any questions, maybe any remarks or questions? So in Gromov's work, actually, he kind of mentions this, that at the time there was this question was being raised. So he said that this is kind of a partial answer to the question of whether you can expect such disks attached to totally real submanifolds of Cn. So I'll define what that is. Question: can we expect attached disks? And L of dimension n in Cn is merely a totally real compact. Let's talk about these, what these are. And
only x coordinate to define the
we are taking only the x
coordinates of.
So perhaps I didn't write this very well. So what I'm saying is, suppose there exists a symplectic embedding, or rather, suppose there exists a smooth embedding P from the abstract n sphere into Cn such that P of Sn, the image, is Lagrangian with respect to omega naught. That's where the proof starts. Okay, the proof starts here. Okay, and this now, for the purpose of this proof, this image itself I'm calling Sn. Okay, so it's not going to look like your standard sphere. It's just a smooth embedding. So it could do weird things, but topologically it's still, in fact, diffeomorphically it's still the sphere. Okay, so I'm just saying that I want to say that there is no smooth embedding whose image is Lagrangian with respect to omega. Okay, so I'm not taking a particular Sn. I'm assuming there is something. I'm taking that Sn. Nevertheless, I will get this disk attached to it, and this argument is a purely topological argument, so it will not matter how the embedding looks. Does that address your concern? Okay. And another thing I will ask you to think about, try to think of some very standard n spheres in Cn and see why they're not Lagrangian. You can also try to attempt something like this, but anyway. Okay, so the question was, can we expect, this is perhaps where this, in some sense, this was in partial response to this question, that if you just have a topological submanifold, can we expect such this? So let me just spend a little bit of time on topological submanifolds, because they are going to be the sort of main subject for us over the next few lectures. So let's. And I'm not going to do this in full generality. I'm just going to do this in CN. And I chose to do it this way because this is a workshop in CR Geometry, and I feel like the following discussion is perhaps a little bit useful. So first, we're just going to do some linear algebra, very basic. There's nothing going on here. Let W in Cn be a real subspace of Cn. Okay. The maximum, I don't know this came up in various lectures, but I don't know if this was kind of discussed very formally, so I might as well do it, and then you can see how it matches up with the discussion that, there's a lot of overlap, but we kind of need different things from these objects, so I'll still go over this. So the maximum complex subspace of W, so remember that W is currently just a real subspace. I haven't told you the dimension. You can take, let's say, real dimension K. And this may or may not borrow some of the complex structure of Cn. So the maximum complex subspace of W is, I will give it some name, HW. And what is this? You just see, you look at W intersection I times 1. Okay, so you just see which are the vectors, which when you multiply by I also remain within W. And so that is kind of, as the name suggests, this is the maximum complex structure that W is borrowing from Cn. Okay? And this may just be the trivial zero vector. It's quite possible that this is the trivial zero vector. So let's just do a little bit of dimensional analysis here. Note that HW is a real subspace of W itself and a complex subspace of C. Okay, so because it's a complex subspace, I can talk about its complex dimension. Okay. So let's just do some quick analysis. So if I look at the dimension, the real dimension of W intersect J W. Okay, so I might switch between I and J. It's a bit annoying. So you kind of do your inclusion exclusion formulas. You get dimension of W plus dimension of IW minus the dimension of the span of, so the space generated by W union IW. That is how you can compute the real dimension of HW over here. Now this guy over here, of course, this is at most 2n. Right? This is at most a dimension of the ambient space. I don't know what this generates, but it's not going to generate more than 2n real dimensions. And so, and this this is just the same as this. So what I get over here is I get that this is greater than or equal to 2 times that real dimension of W minus 2. And so what I get over here is that if I want to look at the complex dimension of maximal complex subspace of W, so W is just a real subspace, I want to know what can be the maximal complex dimension of W. I have some bounds here. So what do I have as an upper bound? Right? I mean, let's say W itself could be a complex subspace, in which case, so what you can say is this is the real dimension of W divided by 2, and of course you may get a non-integer, so we just take the full function of that. So that's an upper bound. This is a lower bound, but this could be negative over here. So divided by 2. Okay, I'm now taking the complex dimension. So it's max 0 times the dimension of W minus 1. Okay, so let me just pause briefly and make sure that everybody is on the same page here. So I have taken a real subspace. I'm looking at the maximal complex subspace. So that's the maximum amount of complex structure you can borrow from CN. I want to see what complex dimension it can have, and you get certain bounds by some very simple a computation like that. Let's just write down some possibilities to get a sense of what's happening here. Okay, so here is the real dimension of W, and this is the min possible complex dimension of HW, and this is the max possible dimension of. Okay, so of course, if your manifold is just 0 or 1 dimensional, if you just have points or a 1 manifold, it just isn't enough space for a complex subspace. You're not going to get anything over here. Now, if your tangent space, your W itself is real dimension 2, then what could happen is that you do J times any I times any of the vectors, you will always exit, or it could be a complex subspace itself. So you get 0 or 1 over here, and this continues till the dimension of the manifold is half the real dimension of the ambient space. So each of these vectors you could hit by I and exit the space. So you could have 0, and then the maximum you can get over here is really coming from the upper boundary. Okay, and something I should remark and you can take as an exercise is that all the intermediate values can occur. Okay, so an exercise for you is that you produce a W. So for each of these, you produce a W, a linear subspace of Cn, so that all the intermediate values are actually achieved as the complex dimension of the maximal complex space. Okay, and so then what happens as soon as you go 1 dimension higher, you now have too many vectors in your subspace. So you will have one complex direction. You just cannot avoid it. But the upper bound sort of remains along the same track. And then maybe a good place to look at hypersurfaces, which is something that Gigi has discussed. There you do get necessarily an n-1 dimension. So if you sort of look at the normal of this plane, then I times that is sort of the only direction which is going to create problems, which we have already discussed. So the situation is there's not much flexibility over here. And then if you are 2 in dimension, then really you won't have another option. Okay, so again, this is something that is worth keeping in mind if you're thinking about CR manifolds. But let me say something over here. So this category, these guys, these are all known as totally real subspaces. So if I have a real linear subspace of Cn, and the maximal complex subspace of that is the trivial subspace, then those are known as totally real subspaces. And this one, when the dimension is n, this is known as maximally a maximal totally real. It's kind of hard, but when you have multiple objectives, it's very complicated.
Yeah, sometimes it's maximum real also.
maximal real subspace, maximal totally real subspace, whatever. So this is going to be the focus of our discussion. I should also mention, I think this came up very briefly because somebody had asked this question. If we are in this situation and there is some question of convention over here. So if my starting dimension is n, and I look at the situations where the minimal dimension is attained, the minimal possible complex dimension is attained, then these are known as generic subspaces. And at least in this setting, this is fine, right? I mean, in the setting of real linear subspaces.
Are they really generic?
Yes, because they can be written as, you can always write them as the intersection of.
But they're special generic.
What does that mean? Wait, hang on. What is special generic?
No, I mean, like if you use the generic in the generic sense, right?
Yeah, not generic in the CR geometry sense, right? Right?
Yeah.
But the point is that at least in this setting, the maximal complex subspace can be written as the transverse intersection of codimension of this many complex hyperplanes. So the generic does.
With a probability 1, if you pick a random subspace of those dimensions, you're gonna get that.
Yeah. So it is generic in that sense, right? And so for me, what matters is really this object here. So if I give you an n-dimensional submanifold of Cn, then at most points the tangent space is going to be a maximal totally real subspace. That's what matters in my discussion. Okay, so in that sense, it is the generic condition, and in fact, and maybe say this properly, it's also it is an open condition. Being totally real is an open condition. Okay, questions at this stage? Yeah, I mean, okay, maybe I didn't want to open this can of worms. So you kind of take this as a definition, okay? And what happens in this case is that if W is generic in this sense, then HW is the transverse intersection of a certain number of complex hyperplanes. How many do you need? You take the codimension of W, this many complex. Okay, so you can think about this statement. You can see why having this, I mean, it's not obvious, but having this dimension implies this and this. But it's not going to play a big role in our discussion. I just wanted to, since I was writing down this table and since this term came up earlier, this is maybe why I just wanted to mention it. And all these objects here, if you want examples, so this subspace over here, where you set all the imaginary parts equal to 0, that is a totally real subspace, for example. Okay, so I'll leave an exercise for the discussion session. Because this exercise actually it's quite useful when you actually want to compute. This is now too small. When you actually want to compute something, this is quite useful. So okay, show that the following following equivalent for. So what is my starting object? I have the span. I take my W to be the span of n, where n are linearly independent vectors. So I take n are linearly independent. Okay, so I just take n are linearly independent vectors. I take the span of that. That gives me an n-dimensional space in Cn, and I want you to show that these three are equivalent. One, that W is totally real. The maximal part comes from the fact that it has the right dimension, so there's nothing to check over there. Two, when you take, these are also V1, how did I say this? Yeah. So when I take the C span of these n vectors, that actually gives me Cn. So not only are they linearly independent, they're actually C linearly independent. So that's kind of a nice way of checking that your your n vectors are actually generating a totally real subspace. And the last useful statement is that there exists a complex affine map, complex linear, across Cn to Cn, such that when I take the image of W, I get this model totally real. Okay, so I'm just saying that you can send any totally real plane, a maximal totally real plane, to the favorite. This is kind of, Rn and Cn is a really nice model. So within the space of totally real planes, you have some transitivity when you hit it by C linear invertible. So this is, I mean, think of it as this is G, L, and C. So the action is transitive. What else did I want to say over here? Maybe I will not say that, and we will move on to some other things about maximally totally real or someone. So okay, so definition. Let M in Cn be a smooth submanifold of real dimension n. Say that M is maximally totally real. So I'll always work with maximally totally real. If tangent space of M, which you view as a linear subspace of Cn. Okay, I'm viewing TPM as a linear subspace of Cn, is maximally totally real when viewed as a linear subspace of Cn, and this happens at all points. So I really need that all tangent spaces are totally real subspaces of Cn. Okay. So maybe before we proceed to the statement I want to make over here, so suppose, example, I can give you this example, I mean, it makes sense. Suppose let L in M omega be a Lagrangian submanifold. And let J be a compatible, almost complex structure on N. So for the purpose, if these words confuse you, take N equal to Cn, omega equal to omega naught, J equal to J. Then my claim is that M is totally real with respect to this complex structure J. So what do I need to check? I need to check that if I take the tangent space at any point of L, then it is a totally real subspace of Cn with this complex structure, okay? Which again you can take to be the standard structure. So, suppose not. So suppose not. I.e., what does that mean? There exists a point in this submanifold such that TPM is not maximally totally real. So when I look at TPM intersect JTPM, it contains a non-zero vector. Okay? It contains a non-zero vector. So it's not totally real. So it has some vector so that when you multiply that vector by JB, that's also going to be inside this space here, H of TPM. Okay? So when I look at V, and I look at JV, so this statement is saying that both V and JV are now inside TPM. And what is J being compatible with omega mean? It means that when I look at this pairing, this has to be positive. Right? That's what compatibility gives us. But I'm taking omega and I'm restricting it to vectors that lie in the tangent space of M. And what is the Lagrangian condition? The Lagrangian condition is that when you take the symplectic form and you only apply it to the tangent vectors, you should get a 0. So this is the Lagrangian condition. This is the compatibility condition. Okay, so that's the contradiction here. And so that means that Lagrangian submanifolds are in particular always totally real. So they are special cases of totally real manifolds. You can't always, okay, maybe let me pause here. These are simple proofs, but there's just a language. So let L equal to the span of, so I'm going to give you, I guess this kind of goes back to Sushil's remarks. So let me give you, let's say, I'm writing my vectors in C2 as vectors in R4. Take the real span of one, let's say, what do I want to take? Let's say 0, 1, 0, 1. Okay. So is L Lagrangian with respect to the standard structure? Remember, the standard structure is nothing but dx1 wedge d by 1 plus dx2 wedge d by 2. So it's a linear subspace, okay? So the tangent space at each point is the linear subspace itself. Don't worry about that bit. I'm just saying that as a subspace, is this Lagrangian? What does that mean? I have to apply omega naught to pairs of vectors coming from this subspace. Am I going to get a vanishing form? Yes.
There is it supposed to be then n is totally real with respect to j, or then L is totally real?
Oh, I'm sorry. Yeah, it's always the submanifold. And then, of course, I have probably created this mess. Going forward, okay. Yeah, so here, is L Lagrangian or not? Yes,
So,
sorry. Okay, back to that.
One clarification. So, in the definition, you defined totally real submanifold for complex for CN, and here are you saying that definition still makes sense?
Yes, so I cheated. I kind of did not. I don't want to define. So the totally real submanifolds discussion going forward is going to be entirely in CN. So if people don't want to think about abstract manifolds, they can start paying attention to these lecture notes from that stage. So this proof, and that's why I'm making this remark, that you can think of this example purely in the standard setting. Okay, so this entire argument will hold. For those of you who are accustomed to thinking about more general manifolds, the same argument tells. So first of all, there is an analogous notion of totally real submanifolds in anything which has an almost complex structure, simply by looking at this intersection. And in that situation also, the compatibility of J with omega is what gives you the connection between Lagrangian and totally real. Okay, but if you don't want to think about that, you go back and write down this argument entirely in this space. The same argument will hold. The advantage of this space is that you can write in coordinates. Given, no, that is not. So you have an omega naught, and it's not always the case, I think, that you can get a compatible almost complex structure. The reason I'm pausing a little bit is because basically you have this triplet, right? You have omega, you have this compatible structure, and then you have the Riemannian metric that comes out of it. So I think when you have two, you can get the third. And in general, there's no problem in constructing a Riemannian metric on any manifold. But I think there is, huh? No, but I think there is some gap. There's some issue. There are manifolds which have they have symplectic structures, but they don't have almost complex structures. So that they just don't have almost complex structures. So forget the question of being compatible. So that means taking a Riemannian metric in a symplectic form, you cannot immediately get an almost compatible.
I think it's a pairwise compatibility condition. And if you have any two, and they
Right, so G, so the Riemannian structure, Riemannian metric you construct has to have something to do with omega, and that's missing. So it's not true that you will always have a J. Okay.
Can you give an example? Let's do what we.
No, okay, I will not say anything because I mean one of the spheres. I mean all the exotic examples come from spheres. So even the other one where you have almost complex but not symplectic, they're basically it's among the spheres that you find this example. Right, but just coming back to Earth, Cn, C2. What is right? I mean, in spheres, we have already rejected spheres as bad objects. They don't even have Lagrangian embeddings, for heaven's sake. So we don't want to live in the land of spheres, but no. So just this simple, is this Lagrangian or not? How do you apply Ex by Gy?
So the first one, I guess, is del by del x1. The second one is.
I mean, so this will basically take the determinant of this plus the determinant of this matrix over here. That's how you apply forms. Okay? Yeah, please. Basic stuff, okay? So this is already going to give you a 1. It's already going to give you a plus. I mean, no point of thinking about almost complex manifolds if you can't apply a 2 form to 2 vectors. Okay, so right, so this matrix is going to give you a 0. This is going to give you a 1. So omega naught acting on u and let's say u1 and u2 is already not 0. So that's already telling you. So let me call this u. Let me call this v. You can see that this is already not 0. So L is not Lagrangian. Standard structure. Is it totally real? So check that L is totally real. Okay, so in general, there are a lot more totally real planes than there are Lagrangian planes in Cn, and this is just C2. And in fact, I had written this statement here, right, that you give me any totally real plane, you can go to the standard one using invertible C linear maps. In the Lagrangian setting, if I only restrict myself to Lagrangian planes, then I can go from one to another using unitary maps. Okay, so that should give you a sense of the restrictions. If I start with my model Rn and I want to take it to a Lagrangian subspace, I have to hit it by a unitary map. Because if I want to take it to a totally real subspace, I can hit it by an arbitrary invertible complex linear map. So that should tell you that one category is much larger than the other. So of course it seems like why are we going to be able to say anything about totally real submanifolds based on a result about Lagrangian submanifolds? So I should make a few more comments about how does one actually work with totally real submanifolds. So there are a few interesting properties.
Can I ask a question back to Blomov's?
Yes.
So what is the proof technique like?
So I'm going to cover that in the sense that so hopefully I will be able to give you, I will cover, so there is a version of this result for totally real manifolds, which I will not state right now because it's a bit of a giveaway. The basic principle in all of these is always that you set up a space of maps. So for us, disks are always attached maps. You set up a space over there, and it's an infinite dimensional space, and you apply some sort of implicit function theorem to get a solution. Okay, so that's just like a one-word synopsis of. So we are basically doing sort of infinite dimensional calculus. Calculus on infinite dimensional manifolds is what we do. But setting up the right space is a bit of a. This is a sticky point because our tendency is to try and work with CK smooth maps. And as some of you may have realized that when you need certain estimates, what you need like an additional holder condition. So my hope is that in the next 3 lectures, I should be able to give you a sense of all these things that go into it. But right, so that's the sort of brief. And that is also the idea behind Gromov's non-squeezing theorem, where he constructs disks. So that was also a question of constructing disks. And I do want to be able to tell you the contrast between the first example that we saw, which is Levy's example, and these kind of, what is different about these results. Okay. So a little bit more. So if all the symplectic geometry is confusing, just focus on the totally real condition. That's the one that we are going to work with. I'll make a few remarks about some facts about totally real manifolds. And these facts are what actually allow us to work with them. Otherwise, it's sort of very difficult to work with just that tangential condition here. So first, locally, after an affine change of coordinates, or a C-linear change of coordinates, C-affine change of coordinates. This is very similar to how UG set up things for hypersurfaces. We can write N as C in Cn. So even though I'm writing it in Cn, it's really happening in a ball around the origin. Okay, this is just a local picture, and I can write y1 to yn, the imaginary part. I can write these as real valued functions on the real coordinates. Where P is a map from Rn to Rn. Again, this is all happening locally. It's smooth. So I'm talking about smooth manifolds. Phi of 0 is 0. I can assume Phi of 0 is 0, and the phi at 0 is also 0. Okay, so the idea is the same. So I'll draw a very quick picture over here. The idea is the same. This comes from exercise 3. Let's say that you want to focus at some point P in your totally real manifold, and your focus is entirely in a neighborhood of P. So obviously you can translate and bring that P to 0. That's not a problem. Translations are allowed because you're allowed affine maps. Now you look at the tangent space over there. That's maximally totally real. We are always working with maximally totally real submanifolds. So the tangent space is going to be a maximal totally real subspace, and you hit it by a C-linear map, and you bring it to Rn equal to 0. Okay, so you just bring everything to this normal, these kind of normal coordinates, and so you get this really nice picture over here, which is that, so think of this as a copy of Rn, and then you kind of have some sort of graph, n-dimensional graph over it, which is your map. So having it in this form actually makes a lot of things very simple. It allows us to check many things. So I'll see how many of those things we can say. So the first one is that if I look at, so assume n is compact. It doesn't matter, but for our discussion, n is always going to be compact. Now, there is something, I mean, if people study domains of holomorphy or Stein manifolds, there's a reason why they also parallelly study totally real manifolds. What is the importance of totally real manifolds? Why do we care? So look at the following map. I take a point Z and I look at the distance of Z from M. Okay, M is a compact set, so I can talk about distance. I'll square it. So always, if you're working with these objects for the purpose, I'm sorry, I'm so bad with letters. So M is now going to be my n-dimensional submanifold because the ambient space is Cn. Okay, so forget about L. M is the new cool kid in town. So we're going to work with M, and it's compact. I can talk about this. And keep in mind that if I'm looking at my model, then what is the distance square function? So if I look at rho What is rho of Z? So if M is just this flat Rn, or you can think of R in C, take n equal to 1, then what is the distance square function of any Z from M? I'm sorry?
Y square.
Yeah, it's just. Okay. So I'm just, I have this flat thing, I have a point Z, and it's just going to be the square of this height over here. Right? Okay. So this guy, first of all, this is a strictly Purvi subharmonic function on some small neighborhood. Small, I'm saying just to emphasize that you cannot expect too much. Small neighborhood. Okay, you did discuss strictly subharmonic functions or? Oh no. Okay. Okay. So
I guess almost.
you almost did. So your, I guess you take the Levy form, whatever, however it has been defined, of this, and that has to be positive, definite, everywhere where this function is defined on all vectors. There's no question of testing certain vectors and not testing certain vectors. Okay, so strictly PSH is basically a notion of convexity, strong convexity for complex analysis. So PSH functions are real value. Note that this is real value. This is in fact a non-negative function. It's actually also smooth. So the square I have put in specifically to make sure that I have something which is smooth all the way. And what will happen is that when you write down, so this is something you can do using local coordinates. Don't try to do this by hand like this. This is a local statement. You go at any point of the manifold, take a ball around it, shift it to this, and then in these coordinates, you can write down the distance square function. We know if somebody gives you a graph, we know how to compute the distance of a point from the graph, right? At least locally, you can try to write down something. And so I'm not going to prove this. I'll put references down, but these guys, if you look at the Levy form, and that's positive definite on CM. Test it on all non-zero vectors, okay? So what is this saying? That if you have something which is totally real, then what you have is some neighborhood of it. I mean, this is a slightly important point from what we are from the point of view that we are going to take. So there is some neighborhood of it, which is given by this yellow region, on which I have a function rho, which is non-negative. It's strictly plurisubharmonic, and its zero set is precisely the manifold that you started with. Okay, so M locally can be written as the zero set of a smooth, strictly plurisubharmonic function. And what does that tell us? If I take the level sets of this, so if I look at something like the sub-level sets, so C is, let's say, positive. If I look at sub-level sets, and most of these are going to be strictly pseudo-convex domains. Okay, so these mostly, these will carve out strictly pseudo-convex. So any totally real manifold always admits a neighborhood basis of strictly pseudo-convex domains. Okay, so sometimes when you want to produce strictly pseudo-convex domains of a particular topology, you can maybe ask, can I start with a totally real manifold and look at a tubular neighborhood of that? The only thing to be careful is that the topology of this, these are not genuinely tubular neighborhoods. Okay, so the topology might change quite a bit, but nevertheless, this is one of the important points over here. Another point over here that I will write down. So when you have an SPSH function, you can look at DDC of rho, and this is going to be a symplectic form. It's actually going to be a scalar form, but I'll not say more about that. So what is happening is, and this vanishes along M. So another thing I want to mention here that even though there are lots of totally real manifolds which will not be Lagrangian with respect to the standard structure, given any totally real manifold, there's always a small neighborhood around it that admits a symplectic structure with respect to which n is Lagrangian. Okay, so I'm not saying that this symplectic structure is the standard structure. I'm not even saying whether this symplectic structure extends to all of Cn. It only lives on a small neighborhood of n, but on that neighborhood, whatever the symplectic structure is, n is Lagrangian with respect to that. So there is some connection, even though totally real are not always Lagrangian with respect to the standard structure. Locally, there is something Lagrangian about totally real manifolds.
What is that?
This guy.
Yeah.
So I'm viewing this as a 1-1 form. It's a 1-1 differential form, and it's positive in that sense. And if you don't know what that means, it's not important because you can just forget about this remark for the moment. It doesn't matter. But it's a 1-1 form, so you can talk about positivity of 1-1 forms because they basically behave like your basically like your Levy form is also something like that. This is, I guess, the Levy form in this case. Okay.
Just a quick question. So how would one think about this condition? So basically saying somehow in this structure it's flat along here.
So when I pull it back, so if I take the inclusion of n into this neighborhood U and I pull back BC rho, then the pullback vanishes, which is the Lagrangian condition.
So
and that's
in this structure is like the Rn.
In this structure, it's like the Rn, exactly. I mean, yes, exactly. And the point is that rho actually vanishes, right? So the gradient, I mean, the BC, this kind of picks up like the tangential derivative of the gradient of rho, so that vanishes.
So it's all pointing in the normal.
Yeah. So
that is like fully harmonic on that particular.
yeah, I guess you can say that. Yeah, stronger, right? No, fine. Yeah, it's pluriharmonic on the totally real. I mean, it's like you're totally real, right? So what does pluriharmonic? Yeah. So there's no complex structure on this end.
Right.
So okay. Maybe one more thing that I should say.
And one more question. So what if we took the sine this is the boundary function and not the square? Is that relevant at all for what? Sorry, I take that back. Again, wrong dimension. There is no sine distance to boundary.
The thing is, there's no inside
Exactly,
outside, right?
Yeah,
so that's yeah.
This is the only thing.
Okay, so I wanted to also make a comment about flattening since this came up with the Levy flat business as well. I want to flatten my totally real manifold locally, but maybe I'll skip that for today and actually go back to, let me see what else did I want to say. Yeah, so we'll worry about flattening later. And actually this Whitney's theorem that Yuji mentioned sort of pops up there as well, but maybe we'll talk about that next time. What I will do is I will sort of now come to the stage where we will compare examples. And just going back to, so observation related to example 1. So what was example 1? At the end of example 1, I took the Siegel upper half space and then I showed you how there are these disks attached to the Siegel upper half space. So here's an observation. Let's say I give you a strictly pseudo-convex domain. And you have this point, which let's say this is the origin. So my claim is that just like with the Siegel upper half space, you're going to be able to find analytic disks that are attached to the boundary. You're going to find a whole bunch of them. I'm not going to write down the precise statement. And you're going to get this family, which is going to shrink to the point that you have chosen. Okay, so no matter what point you choose, you're going to get these families that shrink to that point. And the basic idea, this is not a hard statement. You can hit this by a biholomorphism and make this strictly convex. This is something you did discuss, right? The convexification of strictly, so because you kind of got the quadratic terms, right? Your quadratic terms were like giving you a paraboloid, and then you had higher order terms.
Yeah, but you would still have to get that one to get strictly convex.
Yeah, your
You have to
Levy
get
form.
the-
So this is strictly pseudo-convex. So you have
You have to
lambda.
get the real W square in there somewhere. But you
Yeah,
can
yeah,
also
okay,
put that
sure,
in
sure.
there.
I mean, you can also, right. So you have to do one additional step over there. But it's, yeah, so I'm not going to worry about that. So I'm going to convexify this using a biholomorphism, via a biholomorphism. And this is going to be strictly convex. So it's going to look like this. And here you can literally take slices to get your discs. It's much easier to see the discs in that picture, and you just pull them back. So producing these discs for strictly pseudo-convex domains is not hard. And so I just want you to keep this picture in mind. This is example 1. And whereas in example 2 and example 3, we are never really producing families of discs. Okay, so we are producing what I refer to as large discs. And I'll sort of make that more concrete. So these are kind of local discs that are shrinking to a point, and I want you to sort of compare that with what we were doing in the other set. Okay, so this, so I mean, whenever we talk about discs, we have to inevitably talk about various notions of hulls and convex. Because I didn't want this course to become a course about, polynomial convexity and things like that, but I think it's important to, I mean, this is one of the reasons why people study this. So we are going to talk about various notions of hulls and convexity. So first, so for us, K will always be a compact subset in C. Okay, and yes.
One point maybe. So in this biholomorphic transformation, it is also global change of coordinate. That is kind of important, right?
So it is a change of coordinates on a ball.
Yeah.
So it lives on this full.
Yeah. That
is part of the thing, because we are attaching these discs.
Yeah.
I mean, like, the biholomorphicity has to be preserved on the image of the closure of these discs. Okay, so phi really lives on a ball around the origin. That's the important piece, and then it's going to go and map somewhere over here. And so you can use that to pull back your discs. Okay, so we had this talk about the envelopes of holomorphy of domains in CN, and we kind of want to do something similar with compact sets. We want to think about whether a compact set admits whether all holomorphic functions on compact sets admit analytic continuation to a larger set, which is a rather complicated matter. And so I'm going to write down what is one of the various competing definitions. It's very much an abstract definition, but I'll still write it down so that we have this to compare with how we thought about it for domains. So okay, over here is going to be the set of germs. And what you can do is, if you're really interested in the details, you can look at South's polynomial convexity. It's called polynomial convexity. There's a chapter on holomorphically convex sets. So you can go and look this up. The big contrast is that we are working with it. You want to define the notion of envelope of holomorphy for arbitrary subsets of CN. And what you do is you take the set of germs of holomorphic functions on K. And I'm not going to say what this is, but what you can do is you can take open neighborhoods of K. So here U is going to be an open neighborhood of K. And you can look at the space of holomorphic functions on these open neighborhoods. They are going to, they are basically some sort of Fesher spaces. And you can take the inductive limit. This is all very formal, so I'm not going to discuss this. But there's a way that you can give this space a topology. Okay, that's sort of the important point of view. How do you think about OK? OK are basically continuous functions on K that come as restrictions of holomorphic functions that are defined on some neighborhood of K. The only thing is that the neighborhood may not. If you give me two different functions, they are restrictions of holomorphic functions that live on potentially different neighborhoods of K. So one has to make sense of that. Okay, so it's not like they're all coming from the same neighborhood. So giving this a topology is a little bit of a complicated business. But what you can do over here is this is what is known as a Banach algebra. You can multiply two functions, you can add two functions. It's a vector space, but you can also multiply and get something in K. And so the envelope of holomorphy is a very complicated business. Okay, I'm going to write it down, but I don't want you to worry too much about it. So a character, okay, continuous your functional P from okay C such that it is also multiplicative. So if I look at P of FP, I get P of F times P of G. Okay, so these are multiplicative functionals on OK. And best to think of an example, a really important example is you take a point in K and you evaluate your function over there. Okay, so key example. Small k in capital K, and then I call this evaluation at K. What does it do? It takes F in OK and it evaluates F at K. So this tells you that there is some sort of map from K into the space of characters. I'll call this the I map. So you take any point over here, that's going to give you a character on OK, but OK could have potentially more objects over there. This space is sometimes referred to as the spectrum of this algebra. Okay, so this is a very abstract way of defining hulls, and this is defined as the envelope. So what is this object? I mean, this is kind of ridiculous. What is this? I mean, this is no set. I mean, where does this even live? It's some sort of abstract object. You can give it some topology because you are working with linear functionals. So you can give it a weak star topology. So it does have a topology on it. And it turns out that this is a compact Hausdorff set in the weak star topology. Okay? And the envelope of holomorphy of K is defined as this abstract object. So I'll just denote it by K tilde, and it's this abstract object which is. And one good thing is that we at least have a way of viewing K as sitting inside K tilde via this I map. Okay, so whatever this abstract K tilde object is, it's an annoying object, but at least if I want to think of it as a hull, our capital K is definitely sitting over there. And K is said to be holomorphically convex if this inclusion is a bijection. Okay, so you don't get anything more. There are all the characters on OK come from evaluation at points of K. That's when you say that K is holomorphically convex, which seems a rather scary thing. Yes.
Or the full system.
So K, the envelope of holomorphy is this object.
Yeah.
Okay, and that is nothing but the space of characters on OK. Okay, and you think of capital, so capital K is some set in Cn. This is some abstract space. But the way I think of capital K and K tilde is I take a point here and I look at the evaluation map. Okay, and if you don't get anything more, if there are no more characters than just those, then I say that the set is holomorphically convex. Okay, so it's a rather ugly, hard to work with definition, but so this is a useful fact. Suppose in Cn admits a neighborhood basis of strongly pseudo-convex domains, i.e. they exist domains, so they exist strongly pseudo-convex domains in omega j. So let's say these are parametric, this is indexed by natural numbers such that omega j plus 1 is compactly contained in omega j, and the intersection of these domains gives you precisely a set K. Okay, so if you can write K as the intersection of a nested family of strongly pseudo-convex domains, then K is holomorphic convex. Which, from an intuitive point of view, is simply to say that if you have a function on K, so it's somehow it's a little bit like saying that, let's say I have K, and you give me any point outside K. Let's say I give you a point here, you will always be able to find a holomorphic function on a neighborhood of K that does not analytically continue to Z. Okay, so no matter what Z you give me outside K, I'll always be able to find a small neighborhood of K and a holomorphic function on that neighborhood that you cannot analytically continue to Z. That's what it means in this setting. And the barrier, where are these neighborhoods going to come from? They're going to come from these omega g's, right? You're basically just kind of squeezing your set between strongly pseudo-convex domains. You kind of prevent analytic continuation. This is a one-sided statement. So if something is holomorphically convex in this sense, you cannot always write it as the intersection of strongly pseudo-convex domains, but let's not worry about that.
One question is like, can you also set up a maximal ideas of this group T? In the sense of, can you also keep precise to the whole G and things about it? Because when you talk about the spec,
yes,
it becomes like
maximal idea.
Maximal idea of this group T, and then
but I think that's you're going to get the same thing, right? Here. So I think that's where the language is coming from. Okay, so what does it have to do with all the discussions that we had? So I just want to give you a sense of, my point was to contrast a little bit the two kinds of examples that we saw. So let's just go back to examples. The first is global. I want to compare two types of objects. I want to compare strictly pseudo-convex everything is compact. So I want to compare compact strictly pseudo-convex hypersurfaces, and I want to compare compact totally real manifolds. Those are the two categories in which we have cared about this. And we look at the global and local question. So globally, if M is strictly pseudo-convex hypersurface, then this Hartog's extension has already popped up so many times that we know that. So elements in OK are, what are they going to look like? They're essentially, given any function in OK, you're going to be able to find the corresponding neighborhood U of M, so that F actually lives as a holomorphic function on that. Okay, so you pick an F in OK, there exists a neighborhood depending on F. This is a neighborhood of M such that F extends as a holomorphic function. And these are all going to admit extensions inside. I'm not going to worry about intersection being connected and so on. So I'm going to kind of ignore these topological issues. But sort of the point is that the global picture, if I try to apply this definition to a strongly pseudo-convex hypersurface, then I have lots of extensions. And so these are, sorry?
What is K there?
K is M. Okay, so definitely K is not holomorphically convex. Okay, and maybe while we are, so I'll write down example 2 later. In the global context, let's take K to be a compact, totally real submanifold of CM. Then what did we say? We saw that M can always be written as the intersection of a nested family of strongly pseudo-convex domains. Because we have this SPSH kind of an SPSH defining function. No, it is, we are taking always compact. Okay, I'm always, my examples always, so here also I'm taking M to be compact, and here I'm taking a compact totally. Okay, we'll stick to compact going forward, because all these definitions are only given in the compact setting. Okay, so what this is saying is that, so this implies that M is holomorphically convex. This is the, at least at the global level, there's a contrast over here between considering compact strongly pseudo-convex hypersurfaces versus considering totally real submanifolds. And what is, from the point of view of disks, what is the issue? The issue is that these don't admit holomorphic convexity tells you that these don't admit families of disks shrinking to a point. That's what this is saying. I mean, what is the source in some sense? What is the source over here, right? We saw the local picture. We looked at a strictly pseudo-convex hypersurface locally, and I just restrict myself to a compact piece of that. I take a small neighborhood of that. And what I do know is from the remark I made earlier, is that you have all these disks which eventually enter this yellow region, right? So the continuity at search tells you that you are going to be able to push every holomorphic function on this yellow region to this purple region over here. So it's this shrinking family of disks that is preventing holomorphic convexity of our manifold. Here, the manifold is globally holomorphically convex. You can even make this statement local. So what you do know is you're not going to be able to obtain families like this. So whatever method gives me disks like this, that method doesn't quite work over here. Okay, that's the kind of contrast I'm trying to, because this whole course is about how you produce analytic disks. I gave you all these examples. One might be led to believe that whatever we do over here, why don't we just do that for totally real manifolds? There is this contrasting picture that these kind of families you're not going to get over here. You're not going to get these things that shrink to a point. In fact, I can say even more. Okay, so let me just pause here before I move on to the next statement. I just want to make sure, I mean, these are all to give you a sense of why techniques can differ when you're trying to produce. I mean, on some meta level, the analysis is the idea is the same. You set up the right space, you apply implicit function. But there is some qualitative difference between the kind of disks you can select. And you can work locally. And at the point I'm trying to make with totally real manifolds is you're not going to find anything if you work locally. Okay, that's what makes this problem hard. And I'm going to make an even stronger statement than this over here, very shortly. Questions? By the way, don't be misled. So, in logical statements, don't be misled into thinking that the converse is true. Because I can produce disks locally over here, doesn't immediately give me an answer on the global question. There are lots of situations where you kind of know the presence of local disks, but trying to sort of see the global picture of where these disks go up to, that's kind of a hard problem. Okay, so it's not that local is enough. All I'm trying to say is that there's no point even trying local. Very good. So this is something you already. So basically you predicted the next 10 minutes or whatever. This time I'm going to tell you about polynomial convexity. Note that currently the reason why a Lagrangian is not holomorphically convex. So you're right. You saw this disk. There is a disk there, right? In a Lagrangian submanifold. That is not preventing the manifold from being holomorphically convex. So that's another point. So you mentioned polynomial convexity, which I'll come to very quickly. But a single disk, which is I think the point that Sivaguru was trying to make with that one exercise on A1, right? A single disk is not going to obstruct holomorphic convexity. You can have these large single disks, they're not going to assist with analytic continuation. What they are going to create a problem for is the next notion. So let me write that down here. Maybe I can try and squeeze a little proof. So we talked about holomorphic convexity of a compact set, a sort of slightly easier definition. So definition. So again, K is compact. The polynomially convex hull K hat of K is the set K hat given by all the points in Cn, where if you evaluate the absolute value of any polynomial, it cannot exceed the supremum of this absolute P on capital P. This is true for all polynomials on Cn. So and K is said to be polynomially convex. So you can note very quickly that of course trivially K is going to be in K hat. And if you don't get anything more, then K is said to be polynomially convex. It's very similar to holomorphic convexity. If you don't get anything more in K tilde other than what's coming from K, you have a notion of convexity. I'm not going to go into how is this analogous to classical. Why is the word convexity there? The main reason to study things like this, or even holomorphic convexity, you can think from the point of view of analytic continuation. But another thing you might be interested in is that you have a class of functions. You want to approximate it by nicer functions like polynomials or holomorphic functions or rational functions. So these notions come up from the approximation theoretic point of view. And why this is relevant to us is, in general, it's quite hard to compute the hull of a given compact setting. It's not at all an easy business. I mean, of course, there are simple examples that you can write down, but in general, it's very hard to even detect whether or not something is polynomially convex. But here's a very relevant exercise. Let F be a holomorphic disk attached. K, so that means the boundary is sitting inside K, then this full disk is going to go and sit inside the polynomial hull. Right? So this is an application of the maximum principle. And as soon as somebody can find you a disk like this, then the full disk will go and sit in the hull. Of course, if you have some way of saying that the interior of this disk does not touch K, then you have got extra points in K hat. You immediately got something extra in the hull. So your example is Lagrangian submanifolds are never polynomially convex. A couple of remarks. This was actually already known due to dimensional reasons. You can never have a compact n-dimensional submanifold of Cn that's polynomially convex. That's actually true for topological reasons. But what Gromov tells you is that actually the hull contains a disk, which is a non-trivial statement. This statement is also not true if I change Lagrangian to isotropic. So if I drop the dimension, but I still keep the symplectic condition, this is no longer true. You can have polynomially convex isotropic submanifolds. But the important point is, and this I will maybe not get to prove, and maybe I'll start with that, and you can think about this as an exercise. Let me see if there's anything else I wanted to say. Yeah, so maybe let me make one more remark before I state the final. So suppose you have a polynomially convex. So it's more of an exercise rather than a remark. Suppose K is equal to K hat, then K admits a neighborhood basis of strongly pseudo-convex. Okay, so just using the condition, this is basically can be done using some definitions. Some of you, I mean, strong pseudo-convex is too much. I really just need pseudo-convex domains. I don't need to make them strong. And this in particular tells you that if you have polynomial convexity, you have holomorphic convexity. right? Because you can write your set as the intersection of a nested family of pseudo-convex domains. So that tells you that K has to be K beta also. So one is a stronger notion than the other. And the final comment, which we will be able to prove next time. So we just saw that totally real manifolds at least cannot admit these shrinking families of disks. So let M in Cn. So this is a result. So let's call it a theorem because we will be able to supply a fairly simple proof. Let M of dimension n in Cn be a totally real manifold. Given any point there exists a neighborhood U of P such that when I look at, so I have my totally real manifold, I have a point P, I claim that there is a neighborhood U of P such that when I look at the piece of this totally real manifold inside that neighborhood, I take the closure, that's a compact set, this is always going to be. Okay, so I can always find a small enough neighborhood so that this piece is a polynomially convex set, which in particular tells you not only do you not have these local shrinking families of disks, locally you cannot even have one disk. Okay, so maybe I cannot find this whole family of disks that shrinks to a point, but there are just no small disks. So I cannot expect, so no small disks. Attached to it. Okay, so this is not hard to prove given our local normal form. You have to contrast it with this situation, that of Lagrangian submanifolds. Lagrangian submanifolds are totally real. So there are lots of totally real submanifolds that are globally not polynomially convex, but locally they will always be polynomially convex. So you cannot find, if you want to look for disks, don't focus on neighborhoods of points. The disks have to kind of go and attach themselves in some sort of strange ways. So, I mean, I've already given a lot of exercises, but if you want to think about this, you can try to do this in some straightforward. I mean, this is doable with everything that we have discussed today. You don't need any approximation theory to actually prove it. If you look at books, they will use approximation theory to prove this statement. But next time we will maybe start with a proof because I don't think we proved very much today. I think there were lots of facts. Okay, so where am I going with all of this really? My goal is now from next time onwards, I'm only going to focus on totally real manifolds. I'm going to tell you what is the version of Gromov's theorem for that. There are a few results there. One is that when you regularity of disks, if they're continuous up to the boundary, can we get more? Whether there are disks in the sense of Gromov. If there is one disk, is there stability? Can I find nearby disks? Or if I move my manifold, does the nearby manifold also have disks? So I think, so here's the giveaway. You don't actually get Gromov's full statement. So there are totally real submanifolds to which you will never have an attached disk. So I'll also maybe discuss that example with you, like a simple example where you cannot have these attached disks, even though it's totally real. Okay, I'll stop with that.
This is global, right?
For this totally real, yes, this distance function works globally.
Can you please elaborate this remark?
This remark over here. So what I'm saying is that given a totally real manifold, so let's say you take S1 cross S1 in C2, then Gromov tells us that there's a large disk. So the interior of that disk is going to be in the hull. In fact, if you take S1 cross S1, its hull is the bidisk. It's polynomial. It's very large. But if I focus on one point, I can always find a small neighborhood so that if I look at the piece of the totally real manifold only in that neighborhood, it will be polynomially convex. It will have no hull other than the set itself. So with totally real manifolds, it's very much a global versus local distinction when you want to find disks. Does that answer? So you would have got me my own. I really want this number.
Right, so you did for now.
Yeah, that's true. So we know.
Can you just explain this in a way, like, why it's a non-trivial?
You have a set and you have a sequence of this, these lines, the objects and they converge to this which is in sorry, they lie in the set and they converge to nothing of this pattern. These are all the early this